parallel postulate is one of the most important postulates in geometry. It says, given a line, L, and a point, P, not on that line, there's exactly one line, M, through the point P that is parallel to line L.
Did you get that? So I've got a line and I've got a point, all in the same plane. The parallel postulate says that there's only one line going through the point that's also parallel to the line.
Although an infinite number of lines could go through point P, only one runs parallel to line L. This is what all of Euclidean geometry is based on. Now that we're familiar with the parallel postulate, we can discuss some special facts about parallel and not parallel lines and the angles formed when an intersecting line comes to town.
When two lines are cut by a line, we call this intersecting line a transversal. When the lines are cut by the transversal, 8 different angles are formed. See them all there? There are 4 different ways to categorize these angles. The most general way is corresponding angles. Angles 1 and 5, 2 and 6, 3 and 7, and 4 and 8 are corresponding angles because they're in the same position on either line. They correspond to each other.
Angles 3 and 5 and 4 and 6 are alternate interior angles. They're all interior angles because they're between the two lines. The pairs we mentioned are alternate interior angles because they are on alternate or opposite sides of the transversal.
Angles 1 and 7 and angles 2 and 8 are alternate exterior angles. These guys are all exterior angles because they are on the outside of the lines. Again, the pairs are alternate exterior angles because they are on opposite sides of the transversal.
Angles 3 and 6 and 4 and 5 are same-side interior angles because, well, the pairs are all interior angles on the same side of the transversal.
Now that's a lot of angles for just 2 lines and a transversal, but it's not too tough. Now let's change the situation a little. We have the transversal intersecting a pair of parallel lines. Let's check out the corresponding angles.
What if we measure the corresponding angles in this diagram? Look specifically at angles 1 and 5. They seem to be congruent, right? What about angles 3 and 7? They seem to be congruent as well. So using inductive reasoning, we'll assume the following 2 statements in the form of if P then Q. Our first statement is, if 2 parallel lines are cut by a transversal, then the corresponding angles are congruent. And in the form of if Q then P, our second statement is, if 2 lines are cut by a transversal and the corresponding angles are congruent, then the 2 lines are parallel.
We'll use our deductions here to form a double fact statement that can be summarized as the corresponding angle postulate. Lines are parallel if and only if corresponding angles are congruent. We'll accept this as a postulate because we don't have enough information in our earlier postulates and theorems to prove it yet.
So what we've done is we've used inductive reasoning to develop the corresponding angle postulate. Once we accept this postulate, we can prove theorems about alternate interior angles and about alternate exterior angles.
I accept it.
Okay, great. Let's look at alternate interior angles. The theorem we want to prove is lines are parallel if and only if alternate interior angles are congruent. We need to prove each statement separately because this, like the corresponding angle postulate, is really 2 statements in one. The first statement, the if P then Q part, is if a transversal cuts 2 parallel lines, then the alternate interior angles are congruent. The second statement, if Q then P, is if a transversal that cuts 2 lines creates congruent alternate interior angles, then the lines are parallel. Let's do a proof.
We'll start with the first statement we just identified and prove that, then move on to the second statement. The first statement was, if a transversal cuts 2 parallel lines, then the alternate interior angles are congruent. So given that the lines L and M are parallel, we'll prove that angle 3 is congruent to angle 5. Okay, let's set up our proof table. First, we state our given information. Line L is parallel to line M.
For our second step, we state that angle 1 and angle 5 are congruent. We do this because of the corresponding angle postulate we just talked about. Remember the corresponding angle postulate? It says that corresponding angles, like angles 1 and 5, are congruent.
In our third step, we state angle 1 is congruent to angle 3. The reason we do this is because of the theorem we proved earlier. Vertical angles are congruent, which says, well, that vertical angles, like angles 1 and 3, are congruent.
Our final statement is angle 3 is congruent to angle 5. We can say this because of the transitive property.
In our theorem, we've shown that angle 1 is congruent to both angle 5 and angle 3. Because of this, we can use the transitive property as our reason to say that angles 3 and 5 are congruent to one another. And since angle 5 and angle 3 are congruent alternate interior angles, we've proven our goal. Alternate interior angles are congruent.
Before we go on to the second part of our theorem, notice that we'll be proving the converse of the statement we just proved. And notice that as we prove this second part, we'll apply much of the same reasoning we just used.
So we're going to prove the converse of the alternate angles are congruent theorem, which states the transversal that cuts two lines creates congruent alternate interior angles, then the lines are parallel. To prove our theorem, we're given that angle 3 is congruent to angle 5. We need to prove that lines L and M are parallel.
Let's set up our proof table. Our first step is to state our given information. Angle 3 is congruent to angle 5.
Next, we state that angle 3 is congruent to angle 1. We can do this because angle 3 and angle 1 are vertical angles, and vertical angles are congruent.
Our third statement is angle 1 is congruent to angle 5. This is true because we're applying the transitive property to angle measures.
Notice that we could not have entered corresponding angle postulate as our reason in step number 3. At this stage of the proof, we hadn't proven that corresponding angles are congruent. We do not yet know if the lines are parallel. This is what we're trying to prove. So, be careful with the postulates you start throwing around. That's it.
However, now we know that the corresponding angles are congruent, so it's time to use the corresponding angle postulate. Line L is parallel to line M because of the corresponding angle postulate, and we're done.
So, we've proven each half of the alternate interior angles theorem. Now we can from the mountaintops that lines are parallel if and only if alternate interior angles are congruent.
Moving right along, the alternate exterior angle theorem states that lines are parallel if and only if alternate exterior angles are congruent. We won't prove the alternate exterior angle theorem because it's so similar to the alternate interior theorem, and we wouldn't want to cover this same old territory again. So let's check out the same side interior angle theorem. It's different. How different? Let's take a look.
Remember what same side interior angles are? They're these guys right here. Looking at the diagram, we can see that these angles aren't congruent. It looks like the supplementary, doesn't it? We'll test our observation by proving this theorem. Two lines cut by a transversal are parallel if and only if same side interior angles are supplementary. Like the if and only if statement we just proved, we know that this is really two statements in one. The first statement, the if P then Q part, is if a transversal cuts two parallel lines, then the same side interior angles are supplementary. Let's go ahead and prove this theorem. We'll get to the second part in a minute.
Given that line L is parallel to line M, we want to prove that angles 4 and 5 are supplementary. Okay, let's set up our proof table. Our first step is to state our given information. L is parallel to M.
Next, we state that angle 1 is congruent to angle 5. Our reason is the corresponding angles postulate.
Step 3 is the sum of the measures of angle 1 and angle 4 equals 180. We know this because of the definition of a straight angle.
Step 4. Because angle 1 is congruent to angle 5, we use substitution as our reason for stating that the measure of angle 4 plus the measure of angle 5 equals 180.
Step 5. Two angles whose measures total 180 degrees form supplementary angles, and so angle 4 and angle 5 are supplementary angles. We've proved what we set out to.
So, we've proven half of our proof. Remember, we're proving an if and only if statement, so we must proceed both forward and backward. So, the second statement of the proof is the reverse or the converse of the first.
In the form of if Q then P, our converse statement is if a transversal that cuts two lines creates supplementary same-side interior angles, then the lines are parallel. So, given that angle 4 and angle 5 are supplementary, we'll prove that L is parallel to M.
Our first statement is our given information. Angle 4 and angle 5 are supplementary.
Our second statement is the sum of the measures of angle 4 and angle 5 equals 180 because of the definition of supplementary angles.
Next, we'll state that the sum of the measures of angle 4 and angle 1 equals 180. This is the definition of a straight angle.
In our fourth step, because the equations in step 2 and 3 equal 180, we can set the two equations equal to one another. The sum of the measures of angle 4 and angle 5 equals the sum of the measures of angle 4 and angle 1. This is possible because of the substitution property.
Next, we can drop like terms, the measure of angle 4, on both sides of the equation. Thanks to algebra, this leaves us with the measure of angle 5 equals the measure of angle 1. This also means that angle 5 is congruent to angle 1 because of the definition of congruence.
Our final statement is L is parallel to M. How can we say this? Well, now that we've got angle 5 congruent to angle 1, we can use the corresponding angles postulate.
So, we've proven the same-side interior angles theorem. Lines are parallel if and only if same-side interior angles are supplementary. Now, we've made it to the end of the section. Want to take a look back?
You got it. The parallel postulate is one of the more important postulates. It says that for any line L and point P not on line L, there's exactly one line M through point P that runs parallel to line L.
When a transversal cuts two lines, 8 angles are formed. We categorize them as corresponding angles, alternate interior angles, alternate exterior angles, and same-side interior angles.
The corresponding angle postulate says that lines cut by a transversal are parallel if and only if corresponding angles are congruent. The alternate interior angles theorem states that lines cut by a transversal are parallel if and only if alternate interior angles are congruent.
Likewise, the alternate exterior angles theorem states that lines cut by a transversal are parallel if and only if alternate exterior angles are congruent. The same-side interior angle theorem says that lines cut by a transversal are parallel if and only if same-side interior angles are supplementary. That's it.
Parallel lines are two or more lines that are contained in a plane and never, ever touch.